All right, what's going on, guys? Welcome to another interesting problem on prime logic. The problem I chose for today is a little more complex and deeper than the other problems on the previous video. So if you want to solve this problem, please pause this video because I'm going to solve this problem right now. So let's review the setup here. So we have a simple equilateral triangle here inside it's inscribed inside a circle. Then we have three smaller circles. They appear kind of perfectly snug at each triangle vertex. So they touch both the circle and each other at the same time. So they are the point of tangency is at the vertices of this equilateral triangle, and each of these smaller circles, they are mutually or pairwise tangent to one another. So these three circles are mutually tangent to one another. And here is a twist. There is a little circle that appears at the very center of this large circle, and it is tangent to all of these smaller circles. So this is externally tangent to all of these smaller circles. And it has a name. So this little circle, which is in the area enclosed or bounded by these three smaller circles, it's called a Soddy circle, named after the scientist Frederick Soddy. Our job is to find the area and the radius of this inner Soddy circle in terms of r, which is the radius of the big circle. So, and it is interesting, it is a little deeper because we talk about a Descartes theorem, and it touches Apollonian packings, even number theory a little bit. So one more time, each circle is externally tangent to the large circle, and they are also tangent to other two small circles at the same time, and then we have this inner Soddy circle. So let's name the vertices and the points of tangency as A, B, C, and then the centers of these smaller circles as O1, O2, O3, or O sub 1, and then the center of the large circle is O. So if we connect the centers together, the centers of a smaller circle, we have another equilateral triangle with the sides of twice the r, the radius of the small circles, because they are tangent to one another, and the side of this equilateral triangle is just twice the size of the radius of smaller circles according to the laws of tangency. And then here comes another distance. So this distance from O1 to O, or O1 distance, it is the same as, or it equals, let me write it down here. So O1 distance, it is r, the big R, the radius of the bigger circle, minus the minus the radius of the small circle. So O1 is the radius of the big circle minus the radius of smaller circle. So now at first step is trying to find out the radius of smaller circles in terms of r. So according to the Quartz formula, so imagine there is another circle here with a radius of r minus r, or capital R minus a lowercase r. So the length, the radius is here. Imagine there is another one, which kind of it connects the vertices of this smaller equilateral triangle to this centroid here, or it is also the circumradius. So imagine there is a circle with a radius of r minus r, so this part. And this O2, O3, or O1, O3, it becomes the chord of that circle. So in order to find the chord, so we use the chord formula. Chord formula of any circle equals 2r. So in order to not confuse it with this r, I put it as here. So 2 radius sine theta over 2. So let's now replace it. Chord equals, so 2 radius. Radius is r minus r, and sine theta over 2. So theta, it is an angle that is subtended at a center. So if we connect these two together, so let me just maybe draw that here. So imagine this is the center. And also this bar. So this thing here is r minus r. So let me write it down here. So the chord formula, 2r minus r sine theta over 2. So this angle that is subtended here at the center is just 120 degrees. And theta over 2, 120 over 2 is just 60 degrees. And sine 60 degrees is square root of 3 over 2. And then, so we know that this chord here is equal to 2 small r, right? So we can say 2r equals 2r minus r square root of 3 over 2. So we can cancel this out. So r equals, so let's expand this term here. So r square root of 3 minus r square root of 3 over 2. Then another time 2r equals r square root of 3 minus r square root of 3. So 2r plus r square root of 3 equals r square root of 3. Then we can factor 1r here. So r times 2 plus square root of 3 equals r square root of 3. Then, okay, r equals r square root of 3 over 2 plus square root of 3. So then we can rationalize this fraction by multiplying that by the conjugate of this denominator here. So times, okay, square root of 3. So the conjugate is 2 minus square root of 3, 2 minus square root of 3. Then it becomes, so 2r square root of 3 minus 3r over 4 minus 3, which is 1. Okay, so let me write it down here. So we can say that small r, yeah, so small r equals, so let's factor 1 out. So 1r times 2 square root of 3 minus 3. So, and let me just wipe out the whiteboard here. So this is the relationship of the small circle radius in terms of the big circle radius. So now we found that r equals small circle radius equals the big R times 2 square root of 3 minus 3. Now the next step is trying to find out the radius of this inner Soddy circle, which kind of touches the Descartes theorem. So here we talk about the Descartes, maybe a little bit about the Descartes theorem. So it shows us a powerful formula which relates the curvature or the reciprocals of the radii for the mutually tangent circles. So whenever, according to Descartes' theorem, whenever we have 3 mutually tangent or kissing circles, sometimes it is called also a kissing circles because these circles are kissing one another. So he says that there is a quadratic formula for their curvature. So their curvature, the curvature of the circles equals their reciprocal of the radius, of any radius. So we can, in other terms, the higher, the bigger the radius, the smaller the curvature, and vice versa. The smaller the circle, the radius, the bigger and the higher the curvature. So according to according to Descartes, René Descartes, the philosopher and scientist, so whenever we have these three circles, it satisfies a quadratic formula as such. So k sub 1 plus k sub 2 plus k sub 3 plus k sub 4, so squared of their sums equals twice the sum of each of those squared. So k, again, sub 1 squared plus k sub 2 squared plus k sub 3 squared plus k sub 4 squared. So this is a quadratic formula, and it gives us the radius of the fourth circle. So we have three circles, k sub 1, k sub 2, k sub 3. And according to this formula, we can find the radius of the fourth circle that is tangent to these three circles. So either internally, kind of, or inside them, or outside them. So externally or internally. So according to this formula, because that's a quadratic formula, it gives us two roots. So one is the radius of smaller circle, and another one is the radius of the big circle. So here we can, according to this formula, so this is a little kind of time consuming to replace it, but if we just need to solve for one of these circles, the fourth circle, we can see that it equals, so k sub 1 plus k sub 2 plus k sub 3 plus minus twice square root of, so k1, k2 plus k2, k3 plus k1, k3. So we have all of them, and we just can find it here. So we can see that k sub 4 equals, so what is the curvature of any of those circles? So that's 1 over r, right? So 1 over r plus 1 over r plus 1 over r plus minus twice the square root of, 2 times square root of, so 1 over r times 1 over r is 1 over r squared plus 1 over r squared plus 1 over r squared. So this becomes a 3 over r squared, kind of. Yeah. And it becomes 3 over r. So we can see that k4 equals 3 over r. And we use the plus 1, the plus root here, because it is externally, this inner circle is externally tangent. So if you want to go for the externally inner circle, or the circle that is externally tangent to all of those, you can use a plus sign. If you want to go with the internal, kind of something that is internally tangent to all these three circles, you can go with the minus sign. So here I choose 2 square root of 3 over r squared. So in other words, k4 equals 3 over r plus 2 square root of 3 over r. In other words, it is 3 plus 2 square root of 3 over r. So this is the curvature. It means this is the reciprocal of the radius of this small circle. So we can just write it as the radius is reciprocal of the k4. So radius of r sub 4, let's name it, of a smaller Soddy circle is r over 3 plus 2 square root of 3. So let me just write it down here. So r sub 4 equals r over 3 plus 2 square root of 3. So now let's replace r in this formula. So we can see that r sub 4 equals r 2 square root of 3 minus 3 over 3 plus 2 square root of 3. So we can rationalize this fraction by multiplying that by the conjugate. So r 2 square root of 3 minus 3 over 3 plus 2 square root of 3 times 3 minus 2 square root of 3, 3 minus 2 square root of 3. So now let's apply that here. So r4 equals r. So the denominator here is, so 9 minus, so 3 squared minus this square, so that's 9 minus 4 times 3, it's 12. So 9 minus 12 is minus 3. And then the numerator here, that's, so let's expand it here. So that's 6 square root of 3 minus 4. So this part and this part, minus 4 times 3 minus 9 and plus 6 square root of 3. So here we have r. So 6 square root of 3, 6 square root of 3 minus 12 minus 9. So 12 square root of 3 minus 12 minus 9, which becomes minus 21 over minus 3. So then here r equals, so let's factor 1 out over 3. So it becomes 4, sorry, minus 3 times 4 square root of 3 minus 7. So it becomes so r sub 4 becomes r times 7 minus 4 square root of 3. So this is the radius of the inner Soddy circle. So let me write it down here. R sub 4 equals r times 7 minus 4 square root of 3. So now the last step is just to find out the area of this area of the Soddy circle is just pi r4 square, right? Okay, so let's just replace it. So area becomes pi, the staying squared, so r times 7 minus 4 square root of 3, and the whole thing pi r squared. So we can write it as pi r squared, and this thing squared. So this thing squared is 49 minus 2, 7, 4 square root of 3 plus 48. So let's simplify that. So 49 plus 48, that's 97 minus so 2 times 7, 14 times 4, 56 square root of 3. So that's the answer. That's the final answer, and that's the area of this inner Soddy circle in terms of R. So it means that whenever we have this set up here, we can say that the area of this inner Soddy circle equals to pi r squared, which is the radius of the bigger circle, times 97 minus 56 square root of 3. So that was a little time consuming, that was a little maybe difficult and layered because it contained different approaches, geometry, different theories and theorems. And I want to give you maybe another method in terms of for solving this video. So this was the more kind of step-to-step kind of step-by-step guide for finding this area, but we can, according to this shape and to this setup here, we can say that, so if this is R, so we can say that the radius of this inner Soddy circle, it equals the whole R of the big circle, the radius of the big circle, minus the diameter of this small circle. So we can also write it in this way. We can say that radius of Soddy circle, let's just call it R sub 4. So we can see that R sub 4 equals R, which is the radius of big circle, minus the diameter of this smaller circle. So what's left is the radius of the Soddy circle. We can say that it is minus 2r. And then we can just quickly calculate it. So we have r as 2 square root of 3 minus 3, which we found in the first part of the video. So let's just quickly replace that. R4 equals, so r minus 2r. So 2r, which is r 2 square root of 3 minus 3. So let's expand this term here now. So r sub 4 equals r minus. So r 2 square root of 3, so it is minus 4r minus 4r square root of 3, and another one is minus 2r times minus 3, which is, okay, plus 6r. Plus 6r. So we can say that 6r plus 1r, it's 7r minus 4r square root of 3. Then we can say r sub 4 equals, so let's factor 1r out, r times 7 minus 4 square root of 3. So that was the really fast approach, right? That was purely and totally based on this spatial understanding and spatial geometry and intuitive approach. So even if one doesn't know this Descartes theorem, the Soddy circles and the curvatures and all this type of advanced geometric formula, which took a lot of time to just solve them, and we could have made a lot of mistakes because that included a lot of algebraic computations. So one could say just this r, the radius of inner Soddy circle, equals the radius of the big circle minus the diameter of this circle. Then the approach was the same. So we could find the radius of inner Soddy circle much faster because we kind of obviated the need for going for this Descartes theorem and approach. So no curvature and this type of things, no quadratic formula. So that was really fast, and then we could compute the area of this inner Soddy circle for this radius, which again is pi r squared times 97 minus 56 square root of 3. So that's it. That's going to wrap it up, I think, for today, guys. And we tackled in this video, I think, an interesting geometry puzzle. It was including equilateral triangle. Then we talked about this, we use and utilize this circle tangency conditions, advanced geometric relationship like Descartes Circle Theorem and Soddy circle. And I think this was it was both geometry challenging and algebraic challenging. And we talked about Soddy circles. And it is also, it touches on, so if you're interested in this topic, in this path, you could go deeper and dig deeper and talk and search about this integer curvature, Apollonian circle packings, because in some cases the curvatures, this reciprocal of the radii are of the circles are integers, so it leads to integer circle packing, and also Apollonian circle packing, which is kind of an arrangement for circles where each new circle is tangent to 3 more circles. It forms a fractal-like pattern. It's so beautiful. It also touches more advanced concepts like fourth circles. So there are special cases of mutually tangent circles related to fractions and number theory. And they appear, I think, in continued fractions and also, I think, Fourier sequences. So I hope you enjoyed this video, this deep dive into advanced geometry. If you found this video interesting, so don't forget to like, subscribe, share, and comment if you haven't already. And let me know in the comments if you want more such challenging problems. And as always, I love you guys and I appreciate you guys. And see you on our next video on prime logic.